About the cool content engine. Kind of follows along what we just saw. So, XtremIO has a content engine that makes it unique among its peers in the all-flash array market. It uses this engine as a way to across the cluster. And the only way we can do this is with Flash. The reason is simple, is that we are basically going to just spread data all over the place. And in this way, mean that linear scaling over as we scale across the different bricks in the cluster. If we filled up the first brick before going to the second brick, we'd never get performance greater than a single brick. The reason we have to do this with SSD or flash is because as you spread data all over the place, it would cause the hard drives and the disk heads in those drives to be running back and forth all over because we're basically just random scattering data. And it also would cause an issue with fragmentation, meaning if I write a big file to XtremIO, it's going to break that thing up into 4K chunks and spread those 4K chunks all across the cluster. And if we did that with spinning disk, it would be so fragmented that our latency would go through the roof. But with Flash, we have 0 millisecond latency, meaning I can read two pieces of data in completely different places on the SSD and not take a performance hit. So that's why we can really only do this with Flash. It also reduces hotspots on your solid-state disks, which in turn extends the life. We're not writing to the same disks until we fill them up. We're not overwriting the same ones. We are again spreading load all across the cluster, which evens out that wear, which should be relatively the same across every SSD in the system. Now a diagram. So let's say I have two bricks in my cluster. There they are, brick 1 and brick 2, whatever we want to call them. I'll call them left and right. Then we assign them values. So let me skip ahead a minute. So when you run 4K chunks through SHA-1 algorithm, the hashing algorithm, it spits out some hex values. They're not like this. I believe they're actually longer than this, but this is just an example. Now, those hex values, if you're unfamiliar with hex for some reason, I guess people don't use it as much as they used to, but hex starts at 0, goes to 9, and then A, B, C, D, E, and F. So it's really 0 through F. It looks at the first values in these hash outputs to spread the load across the cluster. So first, if you have one brick, that one brick is responsible through 0 through F. If you have two bricks, it splits them 50-50. If you had 4 bricks, it'll split them like 4 values each, something like that. And the idea is that SHA is actually, really any good hashing algorithm is actually a random number generator, in that as you feed it data, it should kind of give you the same distribution on output for these values. So you should, if I send it a ton of data, I should get relatively the same number of values that start with 0, that start with A, that start with 7, that start with B. So the idea is it's using this hashing algorithm to spread data. So what we care about is that first value there. So we're going to go across the line here. The first one is A, which belongs to the left brick. 5 to the second brick. A back to the first, 1 to the right, 5 to the right, C to the left, 0 to the left, and 3 to the right. So it's not left, right, it all depends on the value. But the idea is that given a normal storage, you're going to average out to be equal across all bricks in the cluster, and then in turn all SSDs in those bricks as well. So it's an interesting way to do this, and it actually makes a lot of sense. I think it's very elegant. Elegant in that it's a very efficient system. Data comes in, 4K chunks, hashed out using SHA-1. It dictates where it goes, and the metadata table is updated. In this way, we don't have to keep a convoluted metadata table. We know very quickly where data is going to live based on the hash, and it's very what they would call deterministic in the algorithm. And as you add additional bricks, if we went from 2 to 4, it would reallocate those hash values and redistribute that data across all 4 bricks. Metadata information is handled by all bricks in a cluster. They don't all hold the entire metadata table. They hold pieces that they need, but the metadata table is redundant in case you lose a brick. So I think some of the things in the metadata table are duplicated on one other, so you have at least 2 copies of the whole thing. Some pieces you actually have 3 copies. I've never seen that broken down. I just know that from some engineering discussions. But what you need to know is that there are redundant copies of the table. All that is kept in sync across that back-end InfiniBand interface. Another question I often get on how things work is I/O requests. So there are some storage arrays here that do allow you to kind of scale out. I'll name EqualLogic, now owned by Dell. So the way Dell EqualLogic was is that you could buy a disk shelf with the controllers in it. And then if you wanted to expand that, you could buy a second one and a third one. And I don't remember how many they go up to. It's been a while since I've worked with EqualLogic. But they did not have a back-end interconnect. All they had were their front-end Ethernet ports because they were iSCSI. The problem you would run into is that if a host requested a piece of data, it would go to whichever controller it was told to connect to first, basically in its pathing list. And it would go to that controller and say, I need this bit of data. And if that controller owned the disks that the data resided on, it would grab the data and turn around and hand it to the host. But if it turned out that that controller did not own the data, and in fact another shelf with another controller did, it would tell the host, you need to go talk to this other guy. So it would get bounced around. The problem is, once you had two shelves, you had a 50-50 chance of asking the correct controller on the first shot. If you had four, you had a 25% chance. So performance would suffer as you added more column nodes or shelves. XtremIO is different. So with this host, I'm going to do a data request to one brick with the data on another. So the server sends the I/O request to the brick. The brick in turn goes and grabs the data over that InfiniBand interconnect and then turns and hands it to the host. So there's no redirection. It's one hop every time. So if it's two, if it's four bricks, doesn't matter. The performance is going to be the same, and it'll always directly go and access that memory. Remember, InfiniBand is using that remote direct memory access, RDMA, very low latency, so the performance is very good even when it has to hop that interconnect. There's also very efficient space usage with XtremIO. I told you you'd see the 4K chunks again later. Everything is done in 4K blocks, and all data is then provisioned when you create a LUN or a volume. Thin provisioning, if you're not familiar with that, basically means that if I carve up a 1 terabyte LUN and give it to a server, I'm not actually carving that out of all available storage. It is not reserved. The host says, ooh, I got a terabyte of space, even though we haven't reserved that much on the back end. We could, it's not uncommon for us to deploy a 10 terabyte brick and carve up 40 or 50 terabyte of storage out of it. Some things like deduplication will keep us from overcommitting too much, but you also need to monitor the array and make sure you're not going too far with your over provisioning. But it's something that is very useful, especially in an all-flash array. And it's something that you also need to keep in mind as you scale this. I suggest that you don't thin provision on your server OS. Like if you use VMware, when you build a new VM, you can tell it to thin provision that VM, meaning I can give it a 500 gigabyte disk, but it only actually uses however much space that virtual machine is actually storing. The problem is, you start doing thin on thin, you can quickly run into a problem where you run out of disk capacity and you weren't expecting it. So with XtremIO, I recommend you don't do thin provisioning on your servers. The 4K block also is the same size as writes on the SSD. So again, we're trying to keep from having to chop up or change data as it flows through the system to maintain performance. So as you add data into a volume that's then provisioned, it is incrementally enlarged in 4K blocks, and that's the same write size on the SSDs. And there's no penalty for reclamation or fragmentation. Flash, 0 millisecond access time. I can take a big file, spread it across disks all over the place or all over pieces of the same disk, and I don't take a penalty due to that fragmentation thanks to the 0 millisecond access time.